What we'll start out with is this image. This is a shaded relief image. And we're going to show a lot of these, so it's worth talking a little bit about what these are. These are made from digital topography. So it's a digital rendering of our topography here in the Champlain Valley. And the yellow dot is on the town of Cornwall. And this kind of flat purple area is Lake Champlain, drifting up here towards Montreal and the St. Lawrence Valley. These are the Adirondacks to our left here. You can see the interesting fracture patterns and some of the higher peaks of the high peaks of the Adirondacks rising up. And as we come across to the east, we come down into the Champlain Valley, through Middlebury area, and then across to the spine of the Green Mountains running north-south here. So I guess I want to explain these more, but hopefully you are also seeing topography and river valleys and lake basins. Those are the types of shapes and patterns we're going to be looking at throughout much of the talk. Also, I'll just say quickly, if you're not muted, please try and mute yourself. Okay, so here we go. This talk's going to have 4 parts. In the first part, we're going to talk about how the bedrock here in Cornwall was made, ancient oceans. In the second part, we're going to talk about how the modern topography was created. So the rise of the Adirondacks and the recent rise of the Green Mountains. In the third part, we're going to talk about glaciation. When did the glaciers come and what impact did they have on the landscape? And then we'll finish a final section talking a little bit about how rivers have reworked our landscape here in Cornwall. So I want to introduce you to this timeline that I'll come back to a few times during the talk, because one of the things we're going to do in this talk is we're going to move freely across geologic timescales. So we're going to start out way back here, about 500 million years ago, right after the rise of modern life, essentially, multicellular shelled organisms. And we're going to take you, that's about 500 million years ago, we're going to take you all the way through. And some of the things we talk about in the end, like rivers and glaciers, are going to essentially be very recent, almost yesterday to a geologist. Take a look at how this timeline is actually one timeline kind of nested within another. So this top part, although it's the same length, represents a lot less time. So it's just really important to stress that this first part of the talk, we're talking about things that happened unimaginably long ago. And they have really nothing to do with what the landscape looks like today, except that the rocks were formed way back then. And this is what we think things looked like back then in the Cambrian and the Ordovician time. We had a pretty good continent going. It was called Laurentia. It was missing much of the west coast and some of the east coast, but the core of the continent was there. You can see the outline of the modern states that someone has taken the liberty to put over this continent. And so we're here in Vermont, and you can see the Adirondacks already exist. The Adirondacks are shown sticking out of the water at this time still. And we're essentially sitting on the edge of the continent, something much like Australia, basically. And we can say that in part because it was tropical. This white line is the approximate location of the equator back then. So the whole continent was actually sitting roughly at the equator, and we were in basically tropical seas. One thing I also like about this figure is if you look off to our east, you'll see some of these island chains. One of these is what we would call the tectonic island arc, which we'll see in a minute is actually going to approach the coastline and actually crash into us and build the proto-Green Mountains. So this view is actually before the Green Mountains were created, but after the Adirondacks were created. So what those look like, this is a diorama from the Field Museum in Chicago. And of course, they looked not much like today. None of the organisms we know today, well, just a few were around. And we had many organisms that have since gone extinct. So all kinds of interesting critters. We had brachiopod shells. These are basically filter feeding clams. These really are very similar to the clams we have today. trilobites, the earliest predatory crab, was crawling around looking for yummy organic material to eat. We had gastropod snails, corals. This is a honeycomb coral right here in the left part of the diorama. These crinoids, these are actually interesting things. These are basically filter feeding, I guess you'd call them animals. They actually use these tentacles to pull in floating organic material. And they're very common fossils. You may find the circular pieces of their stem actually are made of calcium carbonate and calcify quite well. You'll find those as a common fossil. So this is a little view of what the ocean looked like back then. And so going back to the paleogeography, here is a cross section of that margin I was talking about. So, you know, here's the Adirondacks off on the left. Here's the ocean off on the right. And the rocks that we know and love today essentially were deposited along the margin of this. And we sometimes divide it into an inner shelf and an outer shelf. That's not really going to matter in this talk. The only thing that might matter to you is a lot of the best fossils are preserved in what we call the inner shelf. Those are some of the limestones that are preserved at Crown Point today. And the rocks here in Cornwall were a little bit further offshore and ended up being metamorphosed a little bit more. But we're all here on this margin. And here is the stratigraphy. So this is the way that geologists express the stack or the time series of sedimentary rocks that are deposited over time. So the rocks on the very bottom are the first to be deposited in the lower Cambrian. And then as we go up in this column, it's kind of a visual depiction of younger and younger sedimentary rocks being deposited successively on top. And this doesn't have a lot of meaning to you, other than to say this is the section of the Champlain Valley stratigraphy that we have in Cornwall. Everything from the Danby formation up to the, hold on here, up to the Glens Falls limestone. Also in here, we have a bunch of dolostones. These are magnesium carbonates. So the Cutting dolomite, the Bridport dolomite, and those are going to come back to us in a second. So with all of those sedimentary rocks deposited on the shelf, the next thing that happened was this subduction zone actually closed. The intervening ocean basin was subducted back into the mantle, and this tectonic island arc actually approached the margin and crashed into us. And as it did so, it compressed all of these sedimentary rocks and thrust slices of the shelf rocks onto each other, which causes the rocks to be moved laterally and rocks that were further offshore to be placed on top of rocks that were further inshore.
Excuse me, Will.
Of course, this also marks the end of the ocean basin. Around 450 million years ago, that really marks the youngest rocks that we have in the Champlain Valley. Because when this island arc docked, the ocean basin disappeared and it became a mountain range, essentially the Proto-Green Mountains.
Excuse me, Will.
Yeah.
Could I make a quick announcement? Some people are having trouble hearing the presentation because some folks are not muted, and so computer sounds and dogs and various sounds are preventing the computer from letting Will talk. So please mute yourselves, and then I'll be on the chat bar following up with anyone who hasn't muted themselves. Thank you.
The host has the ability to mute everyone.
Yeah, let's see.
Will, if you make me the co-host, I can take care of that.
Sure. I think we're doing okay. I think your announcement probably got it done here, but let's have a look. All right, Mike, you are now co-host and
Great.
And everyone's muted also. All right. I have all the power.
Okay, no more interruptions. Sorry about that.
Oh, no problem. That's great. Okay, so that's where we are. We closed the ocean basin. And so why am I even telling you all this? Why does this even matter? I think it's interesting to think about next time you find bedrock in your yard or in your woods, that's where it came from. It's an ancient, essentially part of an ancient coral reef system. In a more practical sense, these sedimentary rocks also govern our modern topography in the town. And the way they do that is that some of them are harder and more erosion resistant than others. So, and what that means is that those hard rocks tend to form ridges and those weak rocks tend to form valleys. It's not a perfect correlation, but we do see some of that. And here's a depiction of that, right? Here's all the sedimentary rock layers tilted on their side. And you can see some of these resistant brown layers are sticking out as ridge lines. And I guess another important point here is that the orientation, these sedimentary beds are like, they're planar, they're planes in space. And so they have an orientation. And here in our town, that orientation is essentially north-south. So these are running north-south, giving us a lot of north-south ridge lines. I'm actually gonna skip ahead. So if you look at, this is a topographic rendering of Cornwall. Here's Middlebury over here. This is Highway 125 coming off, headed to the west. Here's the yellow dot is the town hall, town center. So that's always going to represent that in every slide that I show you. And you can see Cornwall is kind of divided into these ridges, like here's Ridge Road, here's Bingham Ridge. Here's basically essentially the southern kind of bits of Snake Mountain up here. All of these ridges are oriented north-south, right? And the fundamental reason is because those planar sedimentary beds are oriented north-south. And in this topographic rendering, you can see everywhere you see the rough, streamlined texture here, that is actually bedrock. That's a surefire way you can see bedrock. And the places that look flatter and smoother are the sediments filling in the basins between these bedrock ridges. So really the orientation of these beds is fundamental to our town. It's also worth showing this slide, which is very complicated, but it's really cool. It's a geologic map, and a lot of people have never seen a geologic map before. What it is literally a geologist went around all of Vermont and put boots on the ground everywhere and figured out which rocks are grouped together into the same sedimentary units, which are not, and mapped out all the units and all the faults. So it's quite complicated, but if we look here, this is Middlebury at this yellow dot here. It's Cornwall Center at this yellow dot. This is Bridport. Actually, that dot's a little off, but Bridport over here. Just for your reference, so here's Highway 125 coming across here. Here is 74 coming down through here. And I think that, what do you guys take away from this map? Not a lot, other than to say the geology of Cornwall, what it really is, it's a bunch of thrust slices. So each of these black lines represents a slice of rock that has been compressed and shoved or ramped over the adjacent rock. And what you can see is, in some cases, is when that happens, you actually repeat the stratigraphy. So for example, if we look up here near the kind of Ridge Road and the ledges area, what you'll see is these 1, 2, 3 thrust slices right in a row. And they're repeating this pairing of the Bridport formation and the Middlebury formation. This pink and gray keeps being repeated by these thrust slices. And it's that Bridport formation kind of in this dark pink. That is a dolostone. It's a magnesium carbonate. And it's, in this case, very relatively resistant to erosion and seems to be holding up both the kind of Ridge Road ridge as well as the Bingham Ridge are both kind of underpinned by this Bridport dolostone formation. Another thing I can point out here is over here on the far left, if you can see my cursor, this leftmost thrust fault is what we call the Champlain thrust. So this is a very large thrust fault that actually separates those basically the inner shelf rocks over here from the outer shelf rocks in that original diagram that I showed you. And we're going to see, if you're familiar with the topography of the Champlain Valley, we're going to see that this whole area, if you go west of the Champlain thrust, it's a whole different character. It's much flatter, it's much lower elevation. The rocks are much less metamorphosed. And as you come east to Cornwall, you come across this Champlain thrust front, and the rocks are more metamorphosed and the whole area is higher and rougher. So I think that's it for the geologic map. So to kind of wrap up this first section on like what I would call ancient geology, Cornwall's bedrock was formed in a shallow ocean about 500 million years ago. So a long, long time. That ocean was a coral reef environment that produced a lot of limestones and dolostones. The tectonic collision, so the tectonic collision, created thrust slices and repeats a lot of the geologic units in Cornwall. And a lot of those north-south striking sedimentary units are what really define the ridge, the ridge valley topography in Cornwall. So I guess we'll keep moving here to our second section, which is going to be short, and I'm calling it the rise of the Adirondacks, creating today's relief. And so in terms of our timeline, we're going to jump way, way, way forward in time. So we're going to talk now about the last 10 million years. So we were talking about 500 million years. Now we're talking about 10 million years. So this is stuff that happened recently enough that we still see it manifest in the topography. And what happened? This is an area of active research, and actually is an area that I have been working on the last 3 or 4 years, trying to understand why we do have relief here still. Why do we have the Adirondacks, for example? What we know, there's a lot we could talk about, but the key takeaway is that we now know from seismology, seismologists imaging the Earth's interior, that beneath New England is an area of very warm, very buoyant rocks. So this shows the seismic wave velocity beneath Vermont and the Adirondacks. Essentially, red equals warm and buoyant. Blue equals cold and dense. So what looks like has happened is a lot of heat and fluids and possibly even magma, possibly even melting, has been introduced and occurred directly beneath us quite recently, and probably in the last 10 million years, which has added buoyancy to Earth's crust and has probably caused much of northern New England to rise, giving us, the whites, the greens, the Adirondacks. Here's a cutaway picture of that. You have to imagine that we are sitting on top of this Earth's crust, which is itself a very, very thin crust or coating on top of Earth. And there's a lot of mantle material circulating beneath us. So as we circulate perhaps warm, fresh mantle material beneath New England, it is altering our crust and actually causing the whole region to uplift pretty recently. So what does this mean for us in Cornwall? The main takeaway here is that if we had to kind of think about our position structurally, we are essentially sitting on the floor of the Champlain Valley between the Adirondacks on the left and the Green Mountains on the right. And one possible model for how we came to be in that situation is that the Champlain Valley itself is a downdropped block, which has been dropped down along what are called normal faults or extensional faults along the flank of the Adirondacks to our west and along the Green Mountain front to our east. So to our east, I often talk about the Great Escarpment, that runs from Bristol down to East Middlebury, down to Brandon, this mountain front that you see as you drive along, for example, Highway 116 or Route 7 South. You're driving along this huge escarpment, which probably is a extensional fault. So Cornwall's kind of sitting in this downdrop block, and these other blocks were pushed up by this warm, buoyant material. And so one thing that I've always wondered is, are there smaller extensional basins on the floor of the valley? And I have to say, I've often wondered if the Lemon Fair Basin itself is actually an extensional basin, similar to what I was just talking about. So again, just to orient you, this is Middlebury over here. This is Highway 125. This is the big hill on 125. Here's where 125 crosses the Lemon Fair, right here. And this squiggly line is the Lemon Fair River running northward. And here's the Cornwall Town Hall in yellow dot. So one of the things about this is could the Lemon Fair Valley itself actually be an extensional basin? Where I was just talking about this in terms of this being the whole Champlain Valley, now I'm asking, could the Lemon Fair Valley itself be a smaller version of this? Perhaps flanked by extensional faults on its east and its west side. I don't know that, but it's an interesting idea, and there's a lot of evidence we could discuss to suggest that it's possible. And it might explain why we have this big, broad, flat basin, between these bedrock ridges. One final thing I'll just say is one way we know this has all happened recently is actually through my own research at the college. Over the last 4 years, we've been dating a lot of faults and fractures. And some of those faults and fractures turn up to be less than 10 million years old. And that's a whole different talk that I won't give tonight. But one of my favorite sites actually is in Cornwall. This is a dolostone bed, which is exposed on the north side of Highway 125. So if you're going west on 125, right as you start going down the big hill, down into the Lemon Fair Valley, look to your right as you're going down that hill, and you'll see this bed exposed with these fractures filled with calcite. And so this whole bed, sedimentary bed, was being ripped apart and fractured by probably extensional stress, actually, and we dated that to about 5 million years. So a lot of evidence that some of this young tectonics actually has affected Cornwall, actually has been affecting and perhaps developing relief and topography in Cornwall recently. Okay, so to wrap up that part 2, what we're basically saying is the Adirondack and the Green Mountains were uplifted sometime in the last 10 million years, which is quite recent, actually. Champlain Valley was probably dropped down along extensional faults. These are essentially over by kind of Crown Point, Ticonderoga, and then over by East Middlebury. And the floor of the Champlain Valley itself may contain smaller extensional basins. It's possible the Lemon Fair Valley itself is one, but don't have a lot of direct evidence of that. All right, so we'll keep marching forward in time to the third part of the talk, which is about glaciers, which have sculpted our landscape quite a bit. So to go back to our timeline, glaciers are super recent. So again, we started out 500 million years old. We made the sedimentary rocks. We talked about making some of the topography over the last 10 million years. Glaciers are very recent. Glaciers really come into the picture over the last 1 million years. So basically, literally yesterday to a geologist. And they represent just the tiniest sliver of this timeline. So thin you could hardly depict it, maybe roughly the width of this red arrow. And glaciers are fascinating. I wish we had more time to get into them, but what it really boils down to is over the last about 3 million years, Earth has been oscillating between glacial periods when much of northern hemisphere is covered with ice, and between interglacial periods when most of it is ice-free. So we're really going back and forth between these two states glacial and interglacial. And during those glacial periods, we are lucky enough to get covered by ice. And we know from marine records, mostly from records on the ocean floor, that that ice has advanced down over us probably around 10 times in the last million years. So each of these kind of larger blue spikes right here represents an ice advance, where ice likely came down and covered Vermont. We don't actually know that. We don't have deposits from most of these. There's only a couple places we have slightly older glacial deposits, but we assume based on what the volume of ice was known to be. And here's what that looked like kind of in detail in our area. This was the extent of the Laurentide ice sheet, which covered us from around 96,000 to 14,000 years ago. So this was the most recent ice sheet. Vermont is, so the edge of the ice is in purple here. Down around Long Island, Cape Cod is where some of the terminal moraines are. Vermont is squarely under the ice. Probably 2 or 3 kilometers of ice potentially. So this has a profound effect on the landscape. Everybody associates glaciers with erosion. Everybody wants glaciers to be very erosive. In fact, it's probably more important is the amount of sediment that they deposit on the landscape. And here's an example of that. This is a large glacier in Iceland coming off of an ice cap. And what we see coming off the tip of this glacier is huge, powerful rivers, right? Tons of meltwater and lots of sediment. This whole thing is an apron of fresh sediment, which was all delivered by this river coming out from under this large ice sheet. So, right, these glaciers are grinding up the rock and they're spitting out tons of fresh sediment, which really mantles and covers the landscape in lots of different areas. So we see there's lots of places in Cornwall and Champlain Valley where we do have glacial sediments deposited. Our most famous example in Cornwall is probably this place called Bond Island, and it's an esker. So it's actually, and this is it. So this is Highway 125. This is Route 30 southbound. This north-south road is Route 30 southbound. This is the intersection with Swamp Road or a Creek Road right here, headed over to Otter Creek. So essentially this is South Cornwall. All this flat area is the Cornwall Swamp. Oh yeah, this is Otter Creek over here on the right side of the screen. This is Otter Creek channel. And so Bond Island is a glacial esker. It's a streamlined lobe of sediment that was deposited under the ice, actually. There was the base of the ice had become melted into some kind of cavity, and there was high pressure water flowing through that cavity, lots of sand and gravel being flushed into it. And so we end up with this unique kind of lobate shape. And what's fascinating, right? Look at it just standing on its own, sticking up above the surrounding swamp. So that's one reason that's so unique of an esker, right? Because it's not attached to anything else. And the reason it's not attached to anything else is because it was able to form kind of an isolation within this complex sub-ice plumbing of the ice sheet. And if you've never been here, you should absolutely go. You park, there's a little parking area right off Route 30. It's a nature conservancy, I believe, conserve the land. And you walk out this cool road through the swamp, and you just get up onto this streamlined esker. And it's an absolutely fascinating place. This topography up here, north of it, is also glacial outwash. If you've ever noticed this huge quarry, I don't know how big it is, but it's pretty big. As you head on 30 south, they're sitting in some kind of glaciofluvial, so glacial river gravels there. All right, so okay, so no story would be complete without talking about Lake Vermont. And this is another example of the effect of the glaciers, right, on our landscape. The way this story unfolds is that as the ice is retreating northward, a plug of ice, or a late tongue of the ice sheet, is basically wedged or stuck into the northern part of the Champlain Valley. So this is the ice margin right here. This is supposed to be ice in this picture. This gray stuff down here is the extent of Lake Vermont. Here's Middlebury down here, if you can make it out. Here's Burlington here. So what happened, right, is currently Lake Champlain drains northward into the St. Lawrence. We wedged this ice in the top of the valley and it blocked the drainage, and the whole valley filled up like a bathtub, essentially, for probably only about 500 years or less. Not that long, actually, but long enough to deposit a lot of sediment on the floor of the Champlain Valley. And so that Lake Vermont is pretty short-lived. It's fresh water, but eventually as this ice melts further northward, we're left with the Champlain Sea. And I'm showing that on this diagram, which we've zoomed way out now. This is Hudson Bay up here. This is like the coast of Canada, Newfoundland up here, Labrador, Nova Scotia. All right, so Vermont is down here. And the Champlain Sea, and so the ice margin here is shown by, I think roughly this dotted line essentially kind of shows where the ice margin was, that dashed line. And so the ice here had retreated further north and allowed the ocean to actually rush inward through the St. Lawrence Seaway, and ocean water was actually flooding essentially the whole St. Lawrence Valley to our north, as well as the Champlain Valley and Cornwall. So this was salt water. This had whales in it. This had seals, all kinds of other marine waterfowl. This was an exciting time for Native Americans. Paleo Indians were moving into the area at this time. Many of them presumably were hunting marine mammals and waterfowl in this Champlain Sea. And so to kind of make this real for our area, I've got these two depictions of what this looked like. So just to orient you, this is the Lake Champlain, this flat blue area. All right, this thing is Snake Mountain right here. This is Chipman Hill over here. Unfortunately, Cornwall is kind of cut off. Cornwall is just to the south in this map. This is like the top of Cornwall right here. This is Bristol right over here. And so in this top panel shows Lake Vermont. The water was pretty high. The shoreline was up by Bristol. And actually Cornwall was just solidly underwater. We were just under about 100, 150 feet of water. Then as we moved to the Champlain Sea scenario, the water level dropped a lot. And what's fascinating is the Lemon Fair Valley actually became a marine embayment. So if you look at Snake Mountain here, can I move this? Nope. If you look at Snake Mountain right here, this is the Lemon Fair Valley right here. This is Weybridge. And this, I wish I had a better rendering for you, but this little embayment actually extended south into the Lemon Fair Valley. So where some of us are sitting right now on West Street, we would have literally been on the shoreline of this marine embayment. And I'll show you some examples in a second. This makes it actually a rich archaeological area. Areas along West Street, for example, have been categorized as archaeologically significant due to the large number of, basically Paleo-Indian artifacts that turn up kind of in this area, probably because this was an inland arm of the Champlain Sea. Okay, so that's what it looked like. Why do we care? Lots of reasons that we care. One important reason is that anywhere you have lakes and oceans, deep water, deep calm water, you put down sediments. So this is a picture of lacustrine sediments. These are fine-grained silts and clays. And so these are the types of sediments that you accumulate at the bottom of a lake or an inland sea. And these very fine-grained, a lot of clay. They make very nutrient-rich soils, but they also make very thick, muddy, dense soils. They're also easy for rivers to erode. So they create rivers that have certain characteristics and often very muddy water, like Lemon Fair itself. So, you know, bringing this back to Cornwall and thinking about this, and actually this probably isn't the best example, but we can see these lacustrine sediments and other glacial derived sediments in the modern landscape, the modern topography. And one thing that reveals it is the pattern of river dissection, the way that rivers look in map view. And so to illustrate that, this is a shaded relief image of central Cornwall. So again, here's the town center in the yellow dot. This is Route 74 cutting south. This is the intersection of, I guess, West Cornwall Village right here. This is Bingham right here, Bingham Street. And this is Beaver Brook. We're looking straight down on Beaver Brook. And so keep in mind from our previous kind of information, we know that this Bingham Ridge is probably underpinned by bedrock at some level. And we see some of these bedrock ridge lines over here. But the intervening area is very smooth. We're getting a lot of these lobate features. We're getting a lot of these dendritic patterns, these gullying, headward gullying of Beaver Brook up into the flanks of the valleys. We're seeing over widened parts of the valleys where, you know, this small creek has widened these valleys quite a bit. And we see the creek itself is actually meandering, lots of cut banks you can see. So all of this is just classic like textural evidence for, you know, streams that are cutting into unconsolidated sediment. In this case, it's probably mostly lacustrine sediment, although there's probably other glacial fluvial stuff. The main point is it's mostly not bedrock. And we can really see that in the texture, and it has a lot of other implications also for water quality, you know, soil stability, stuff like that. All right, so here's another example of lacustrine features. So now we are looking at shaded relief on the, basically near Lemon Fair Road. So this is Highway 125 coming along here. This is going down the big hill on 125. This is Lemon Fair Road splitting off to the north right here. This is James Road going north, and this is Cider Mill going south here. So that's where we are. And this is the Lemon Fair down here. This Lemon Fair is making its way. And so the reason I included this, there's lots of cool things happening here, like anybody's guess what's going on kind of in the middle part of this image here. But what I believe you can see here is very faintly, if you look at this little green bench, it's kind of flat coming along here. This is likely the Champlain Sea shoreline running through here, where you get this kind of flat bench and then it kind of abruptly slopes off. That's kind of a classic texture for Champlain Sea shoreline. We can see in some places some gullying up into it, suggesting it is finer grained sediments. Not certain, but that's likely an example of the Champlain Sea shoreline there. And we can also see it hints of it down near, this is Route 74, where Route 74 intersects West Street. And then Route 74 itself goes down this big hill and crosses the Lemon Fair. And you can also see hints of this shoreline here near, you know, kind of below the road. And you can see these linear features running north-south. You can see again this kind of bench, which then slopes off. You can see it's being gullied and dissected. And it continues down to here. So I suspect that's the Champlain Sea shoreline running kind of sub-parallel to West Street. And you don't have to work too hard to imagine, you know, Paleo Indians sitting, hunting, living essentially just above these shorelines, kind of, roughly along West Street or other parts of Cornwall. All right, so I'm going to skip all that. So to wrap up part 3, what we could say about glaciers is that ice sheets have advanced over Cornwall about 10 times in the last 1 million years. Glacial outwash has filled in ancient river networks and flattened the terrain. One thing we're going to skip in this talk is the idea that the floor of the Champlain Valley used to have deeper river valleys in a whole different interconnected river network than it has today. Much of that has been filled. All of that's been filled with glacial sediments, we think, and is buried down there somewhere. We have streamlined topography. I didn't really point that out, but that's pretty common. We see streamlined topography everywhere. Things like stony upland soils and more clay-rich lowland soils. Lake Vermont and the Champlain Sea has filled those lowlands with sediment, giving us clay and silt-rich soils in our lowlands. And, if you ever talk to farmers way out in, Panton and Addison, they were even deeper under the Champlain Sea. And that's where you find the thickest clay soils in the Champlain Valley. So our soils are nothing compared to the clay they have out there in the deeper parts of the Champlain Sea. All right, so let's move towards wrapping up here with some words about rivers. And, we're moving forward in time still, right? Glaciers are a very recent thing, but rivers are even more recent and they're ongoing, which makes them very exciting. And they've really inherited the landscape that was left behind by the glaciers, and they are modifying it today. And we can see evidence of that modification. I'll show you in a second. But again, now we're literally up to the modern time. Rivers have affected our landscape over the last 10,000 years and are continuing to do so today. So rivers are cool. They kind of bridge like geologic time with modern time and are relevant to both. So one thing you need to know about rivers before we show some examples is rivers are living things. They actually respond to external forcings and they record those forcings in their shape and their morphology. And one very common way we interrogate the history of rivers is by looking at the river profiles. So we'll look at, make graphs of the downstream distance along the river. That's the x-axis versus the channel elevation, so the elevation of the river. And we see that almost all rivers start out steep in their headwaters, and they get gentler and shallower as they come into their downstream areas. Another rule of rivers is that they all end at what we call a base level, which can be a lake, it can be an ocean, it can even be another larger river. And so the rivers can never cut downwards below their base level, right? Because a river can't cut down below the surface of a lake. It doesn't have the energy to do that. And so, rivers are constantly wanting to get towards some equilibrium gradient, such as shown in this cartoon. If they have too much slope, if they're too steep along their channel, they cut down, they actually erode the channel and make it shallower. If they're not steep enough, right? If they're too gentle, the gradient is too gentle, they cannot transport their sediment and they actually aggrade. They actually pile up their own sediment and essentially drown in their own sediment, which this aggradation essentially ultimately actually increases the average slope because it kind of connects them up to their hinterland. So by looking at areas where rivers have cut down or where rivers have aggraded, we can start to learn about what was forcing them over time. And here's two examples. So one classic sign of aggradation is what we call an alluvial channel, where rivers run over their own sediment, basically. So, here's a shot of the Lemon Fair near Route 74. By the way, I think both these shots are from Matt Witten. Forgot to credit him here. And taken Matt Witten of the ACRW, Addison County River Watch. And actually, these are two of our Middlebury students sampling for the River Watch here. But anyway, so this left picture shows an alluvial channel. There's no bedrock in sight, right? This river it brought this sediment here to make this floodplain land, and it is now flowing through its own sediment, right? So that's what we call an alluvial channel. Look how flat it is. They're really characterized by lots of meandering, large, extensive, connected floodplains, right? That's classic like alluvial topography. In contrast, if we have incision, the river's cutting down, we actually get bedrock channels. So wherever you see a river running over bedrock, that's a surefire sign that that river is actually cutting downward. It's trying to cut down and cut into that bedrock. It's already stripped off all the sediment. And so interesting, the Lemon Fair actually has some areas of bedrock incision as well. As you go upstream from Whistle Pig, so this is not a great photo, but it's looking upstream from Whistle Pig up towards the Richville Reservoir, you actually see the Lemon Fair cutting down through kind of a bedrock gorge in this area. So we see that because of the complex glacial topography, these rivers can go quickly from areas of incision and bedrock channels to areas of aggradation and alluvial channels. So one final general concept, and then we'll kind of wrap up, is one thing is that rivers do not want to be they don't want to be incising. They don't want to generally be running over their own bedrock. And in fact, that can be a sign of what we call disequilibrium, that something has disturbed the river profile. So here's an example here. We have a graded river. It's very smooth, running out to its base level at the ocean. Then in this example, what we did is we put in a fault. This is an extensional normal fault. So the left side has dropped down relative to the right side. And we created this cliff as we dropped the left side down. And that cliff creates a waterfall, or what's called a Knick point in river terminology. It's an area of oversteepened slope, and it's not equilibrium. The river, it's not natural. The river has too much energy. It's going to try to cut downward right there over time, and it will do so. Eventually, it may cut a canyon or a gorge, as is shown in this panel C. There's usually white water associated with it, rapids, right? And so this type of adjustment, and then eventually it will go back to being a graded stream, right? If you give it enough time and you don't give it any external forcings, it will go back to a new graded profile. But if we catch rivers that have waterfalls, there's some reason, there's always a reason that a river would have a waterfall or a gorge, right? Something has disturbed it relatively recently. And that's really where I'm going to try to wrap this talk up, is by zooming out a little bit and looking at the path of Otter Creek and asking the question, why does Otter Creek have so many waterfalls? It's quite a mystery. And so just to orient us again, so the blue line is Otter Creek, yellow dot is Cornwall Town Hall, red dot is Middlebury. This is Snake Mountain over here. This is East Middlebury over here. So one of the things we see as we zoom to this level is Otter Creek is a weird beast. It flows for miles through this Cornwall swamp, this low-lying wetland, right? Where the gradient of the river is extremely low. It's an alluvial channel. It's flowing over its own sediment. Clearly here, Otter Creek is filling up some pre-existing basin. There's some probably structural basin, or maybe it's a glacially eroded basin that Otter Creek is filling up with sediment. And once it did that, once it filled it all up, it was able to continue flowing. And but then past Middlebury, weird things start to happen. It transitions into being a bedrock channel, right? We're at about Middlebury, you head down to Belden's Falls, I'm forgetting the names of all the falls, but multiple falls, multiple hydro stations as you come down towards Weybridge. And actually I have a picture of that. Here's the profile. So this is the longitudinal profile of Otter Creek. Point number 1 is located up in the Cornwall Swamp. Point number 7 is located down by Quaker Smith Road and Weybridge. And between, basically between Cornwall Swamp and Quaker Smith Road, Otter Creek drops about 70 meters, 60 meters. It's a lot over all these waterfalls. And it's not an equilibrium, right? If you had given Otter Creek 100 million years, 200 million years, and none of these waterfalls would be there. They speak to a modern change or a modern forcing. And we're not sure what that is exactly. Keep in mind, we did raise the possibility earlier that the Lemon Fair is a modern extensional basin. So it's possible that basically this eastern edge of the Lemon Fair Valley was simply dropped down, and Otter Creek is responding by cutting headward up towards Middlebury. There's another possibility, which is maybe simpler and less probably controversial, is that what if the Otter Creek is only recently been deflected onto this path? And actually, what if it used to flow through the Lemon Fair Valley? And this is a very real possibility. If you follow the Lemon Fair up, this is the Lemon Fair in this lighter blue, and it is sitting in this huge broad valley, right? It's very flat, it's very puzzling. It's kind of a weak stream that's kind of occupying this like incredibly well-developed valley. And if you follow it up kind of through Richville Reservoir here, you actually can trace it back, and actually some of its headwaters almost touch Otter Creek down in, I guess, Whiting Lester area. So one idea is that, at times in these previous glacial cycles, Otter Creek would have actually flowed, kind of turned to the west and flowed down through the Lemon Fair Valley. And that perhaps only recently, glacial sediments, deposition of glacial sediments perhaps deflected it onto its current course. And, the sequence of waterfalls below Middlebury essentially represents Otter Creek kind of adjusting to its relatively new course, its relatively new path down onto the floor of the valley. So something to think about as you gaze over Lemon Fair Valley is has it always been such a a sad little stream, or was it once the mighty Otter Creek flowing through there? So, okay, I have no idea how long this is all taken, hopefully not too long, but to wrap up the fourth part of the talk, we know that modern rivers inherited a complex topography, in many cases a disequilibrium topography, and we see a lot of evidence that they're adjusting to that. Rivers are cutting easily into glacial outwash and lake sediments. We saw that in the previous part of the talk. So wherever you see gullies, for sure you're dealing with glacial sediments. Rivers fill existing basins with alluvial sediment. So a lot of our flat basins like the Cornwall Swamp, the Lemon Fair Valley, those really probably represent older basins that have been basically filled with river sediment and made flat. And we see Knick zones where Otter Creek may have been rerouted through Middlebury maybe recently. So that is the end of my remarks, and I hope I have left enough time for questions. Thank you all so much for listening, and really looking forward to hearing from the many experts we have in the audience here tonight, or any questions at all you might have. Thanks.